And we want to have an interesting discussion in line with this. And this is, we want to go and discuss about the Actuary and IBNR techniques, a machine learning approach. And to take us through this particular session, we have the Assistant Actuarial Manager, that is QED, Actuaries and Consultants. This is none other than Cesar Balona, who will also be joined by the Associate Director, R&D, Special Projects QED, Actuaries and Consultants. This is none other than Ronald Richman. So we're looking forward to this particular conversation, and we want to hear from them and see how it goes from there. So over to you, Cesar, and Ronald, take it over from there.
Hello, and thank you for joining our presentation on the Actuary and IBNR techniques, a machine learning approach to IBNR reserving. My name is Cesar Balona, and I wrote this paper with Ronald Richman, who unfortunately can't join us today. But we are both actuaries at QED Actuaries and Consultants, and we hope that our presentation today and our paper can bring some further insight into IBNR reserving and prove valuable to you in your day-to-day work, and also spur on some more research on the topic further. So let's jump right into it. So in the presentation, what we'll take you through is just a bit of background on why we wrote the paper. We'll then look at the machine learning approach to IBNR reserving, which is the main idea of the paper. And then we'll look at one of the case studies from the paper, case study 2, and then we will conclude with some final remarks. So in terms of background of why we wrote this paper, traditionally with IBNR reserving, you use subjective expert judgment and heuristics to select a reserving method and the parameters of the method, for example, the loss ratio or how to calculate your loss development factors. So it brings forth the question of how scientific is this process, and can we measure the impact of these subjective choices on how well we predict future claims. So one thing that we as actuaries do is we examine performance next year or next quarter with the AVE result. But often the focus is on whether our reserves are enough and not necessarily on whether they are accurate. And there's in fact limited guidance on which techniques to choose and what parameters to use for these techniques beyond just your run-of-the-mill industry rule of thumb. So in terms of modern requirements of reserving, we need a little bit more. So for example, we often need to determine the best estimate reserve. But what exactly does this mean, the best estimate reserve? So Solvency II and SAM from South Africa say the best estimate shall correspond to the probability weighted average of the future cash flows, taking into account the time value of money. But in fact, it's impossible to know what the probability distribution of the claims actually is. So our suggestion then is to find a scientific basis on which to ensure that the expected value of the AVE result over time is as close to zero as possible, meaning you're minimizing your error and maximizing your predictive accuracy. So less dependence on judgment and rules of thumb, and more focus on accuracy. So ensuring that our choices are correct over time. So now we'll just jump into the main idea of our paper, the machine learning approach to IBNR reserving. So the ML approach to selecting methods and parameters, so when you're fitting a standard machine learning model, what you would typically do is you would take your training data and you would split it into a training and a testing subset. And you would then fit your model and chosen parameter on the training subset and then assess performance on the testing subset. And this would give you a list of your models and the parameters and the associated performance of that model and parameter on the testing subset. And you would simply then, from this list, just choose the model and parameters that result in the best predictive performance on the unseen test subset. So what we do in our paper is we apply this approach to traditional IBNR reserving. So that is to say, we define a set of IBNR calculation methodologies, such as the chain ladder, the BF, and the Cape Cod, and the associated parameters that go along with them. And we fit these methodologies on sub-triangles, starting from a small initial triangle, and then increasing the triangle by one diagonal each calendar year until the end of the available data. And at each of these sub-triangles, we calculate the performance of that methodology and parameter on the immediate next training diagonal, calendar diagonal, using some performance metric, such as the AVE or the claims development result. And I'll touch on these metrics a little bit more. And we basically then select the methodology that results in the best score across all sub-triangles. So if we were to look at this visually, if you look at the triangle on screen and you take the blue initial triangle and the green training data and you look at that full triangle, that's typically what you'd have with your reserving exercise. So that's what you'd use when determining reserves. And the reserves when determining ultimate claims and reserves. And then the claim payments you're essentially trying to predict are the yellow out of sample data on the bottom right hand triangle. And in our paper, we use triangles where we actually know the out of sample data, so we can assess the true performance of the methodologies and the selected algorithms, the selected methodology from our algorithm. So briefly again, we start from that initial triangle and we fit the methodology, and then we step forward, we measure performance on that first training diagonal. Then we step forward, include that training diagonal we measured performance on previously in the initial triangle, fit again, measure on the next diagonal, and we step forward in this way right until the end of the training data. So going back to those performance metrics, the question is, what performance metric do we use? And I listed two, the AVE and the claims development result. So the AVE is the natural choice that we start with because we use it typically in our reserving exercises when assessing our performance previously. And if you think about it, it ensures that predictive accuracy is maximized because basically you're minimizing your actual minus your expected. So if you minimize that, you're maximizing predictive accuracy. But the catch there is that this can cause instability in our reserves over time. So we need consistency too. And that's where the claims development result comes in. So the claims development result is essentially the AVE plus change in your IBNR reserve estimate between calendar periods. So what you're doing is you're essentially adding a penalty to your AVE, which is the change in your IBNR reserve. So if your IBNR reserve is changing wildly from one period to the next, it acts as a penalty and it increases your claims development result or your score metric. And what we're trying to do is minimize that score metric. So if we're minimizing our AVE and we're minimizing our change in IBNR, what we're doing is we're ensuring predictive accuracy is maximized, but also at the same time that our reserves are stable over time. And this is also equivalent mathematically to minimizing the change in ultimate claims over calendar periods. So now we'll just briefly go through the results of one of our case studies from the paper, case study 2. And in this case study, we essentially apply our approach to choosing the optimal methodology to the triangle, and we consider three basic methods: the chain ladder, the BF, and the Cape Cod. So across all our case studies in the paper, we selected from a parameter space which will look very similar to this. So they're not all the same, but they would all look very similar to what we see on screen now. So For the first 3 rows, the parameters are the same across all methods, so across the chain ladder, the BF, and the Cape Cod. And these relate to how we calculate the loss development factors. And so for the first 2 rows, we choose whether we drop the highest and the lowest loss development factors. And the third row, we choose over how many accident periods we calculate the loss development factor over. So for example, for 5, you might use the most recent 5 accident periods, or you might use all the available accident periods to calculate your loss development factor. Then the second last row is the parameter only for the BF method. So it's the a priori loss ratio. So this one only applies when using the BF method. And there we typically select between 40% and 60% in steps of 1%, but this range will depend on the underlying business. And then for the Cape Cod, we choose the decay parameter from 0 until 1 in increments of 0.05. So this is typically what the parameter space will look like across all the triangles. So looking at case study 2, it's a long tail liability line. And if you look at the triangle, you can see the initial blue triangle in the top left. And then from 2012 Q1 up until 2014 Q4 are training diagonals over which we assess the performance. And you can see that it's not a trivial triangle to reserve for. There are some nice little catches here and there. So if you look at the first development period, you'll see the claims amount varies quite a bit over the triangle. And in fact, there's even a few spots here and there where you'll see some negative development. So it's quite an interesting case study. So when applying our machine learning approach to select the methodology and parameters, we compared our chosen methodologies to a basic Cape Cod, where we did not, so looking at the top table, the first column, that's our comparison, so the basic Cape Cod, where we do not drop high or low development factors. And the number of periods over which we calculate these development factors is 21, which in this case is all the available development periods or accident periods. The a priori doesn't apply for the Cape Cod, so that's not applicable. And then we use the rule of thumb of 75% for the decay parameter. So this is a very good, strong base to compare against and is one of the best practice reserving methodologies. So using our algorithm, we assessed when minimizing the AVE score and we assessed when minimizing the CDR score. So in minimizing the AVE score, we saw that, again, we chose not to drop high or low development factors, but we opted for a much lower, or the algorithm opted for a much lower number of development periods over which to calculate the loss development factors. And in fact, it didn't actually choose a Cape Cod or a chain ladder, it chose the BF method as the optimal methodology with an a priori loss ratio of 46%. And then looking at minimizing the CDR result, the far right column of the top table, we see it chooses very similar. Again, we don't drop high or low loss development factors, and we calculate our loss development factors over the most recent 11 accident periods, so quite similar to minimizing the AVE. And again, we choose the BF method with an a priori loss ratio of 41%. So looking at the bottom table, we assess the scores on the true unseen data. So we assess the true performance of these models. And we see that with the basic Cape Cod approach, we get a root mean squared error of about 3,200. And then minimizing the AVE performs a lot better, about 20% better, with a root mean square error of 2,500 about. And then minimizing the CDR, better than the basic Cape Cod, but not quite as good as the AVE at 9% lower. And then if we look at the far right column, what we see there is we rank these models out of all the models in the parameter space. So if you remember the parameter space, we had all these different parameters we could vary across the 3 methodologies, the BF, chain ladder, and Cape Cod. And that resulted in a total parameter space of about 1,848 different models that we could fit. so different methodologies and parameter choices. And then we ranked the true performance of these on the out-of-sample data, and we saw that the basic Cape Cod was a little bit worse than the median, so around 1,073 out of the total models. Minimizing the AVE performing very well right on that bottom quartile, and then minimizing the CDR a little bit worse than minimizing the AVE, but better than the median model. So looking at the actual AVE, so here we have two graphs showing the AVE over the accident quarters of the optimal models that our algorithm found against the basic Cape Cod. So on the left-hand side, we see our model where we minimize the AVE score, and we see that up until the latest few accident quarters, we actually perform very similarly to the basic Cape Cod. And in the most recent few accident quarters, we see that our optimized model tends to under-reserve a little bit less than the basic Cape Cod model. And then looking at minimizing the CDR score, again, a very similar view there, except for the most recent few quarters where, again, we under-reserve a little bit less, but the amount of under-reserving is a little bit less efficient than minimizing the AVE score. And then looking at the box plot on the right, this is where we have all the models in our parameter space, and we see that minimizing the AVE score, the dark blue dot, performs right on that quartile. So a very strong model there out of our total model space. And now we'll just close off with some concluding remarks. So what have we done in our paper? Essentially, we present a framework for selecting reserving models that are expected to perform well in predicting out-of-sample claims development experience. And we see this and we demonstrate this in our paper. So in our paper, we fit on 3 example triangles. In this presentation, I only presented 1. But we see that on these triangles, our proposal performs relatively well, often better than your traditional approaches and ranking quite highly out of the total model space. So we conclude then that scoring reserving models based on historic claims development data provides a useful way of determining which models are likely to predict future development well. And finally, our framework provides an objective way to select methods that produce best estimate IBNR reserves. So thank you for your time, and we hope that the findings of our paper prove valuable to you and that you use these findings in your work. And we'd be happy for you to reach out to us. I'll put our contact details on the next slide, and happy for you to reach out to us to discuss further if you like. And I've provided the link to the paper there as well, so you can go and read the full paper and look at the full results. And thank you to the Actuarial Society of Kenya for allowing us to present and giving us the platform to present our results and furthering research and furthering the actuarial profession. So on behalf of Ronald Richman and myself, thank you for your time, and have a great day further.